Okay, Jeranism, you asked it to be explained, so here we go. Your first example shows a blue marble being affected by the gravity of the Earth and a big rock. So on my graphic, we have a big spherical rock which you suggest to be 5 miles wide. I also have some knowns listed. First, we have the acceleration of the gravity on the Earth, which is on average about 9.8 meters per second squared on and near the surface of the Earth. Next, we have P, which should be rho, but the program I use doesn't like Greek characters, and that represents the mean density of the Earth, which we will use as the same density for the big rock so that things are consistent. At the top is the gravitational law constant, and on the right are the two formulas. One showing the acceleration an object receives based on the mass that the object is pulling on it has, and the radius or distance from the center of the mass of that object. And next, the formula for the volume of the sphere. So knowing the size of your rock as 5 miles in diameter, we can use the volume formula to get a volume of approximately 2.726 times 10 to the 17th power centimeters cubed. And I converted it into centimeters because it is what most scientific measurements and calculations are made in as the metric system. And using the density, we can figure out a mass for the rock as approximately 1.5 times 10 to the 15th kilograms. Now to figure out the acceleration that the rock will pose on the marble, we need a distance or radius. So let's say that the rock is dropped from 5 miles in the air and at a distance of 5 miles from the center of that rock. We use our known mass and now known radius with the gravitational law constant to determine the acceleration of that marble, which is approximately 0.00155 meters per second squared. Now let's see what will happen when we drop this marble. First, we need to figure out how long it will take to reach the Earth. Using this equation, the final distance or position equals the acceleration times time squared plus the initial velocity times time plus the initial position. Knowing that the initial velocity is 0 and the final position to be at the ground, which is 0, and since the force of gravity is down, which is in the negative direction, we plug this information into the formula and can isolate the variable t to get 28.95 seconds. This is, of course, given that this is in a vacuum. If not, effects of the air and air resistance, wind speed, and rotation of the object would throw all these calculations off. Now, knowing that it would take 29 seconds to fall to the Earth, we can figure out how much it would move towards the rock using the same equation, but using 0 as the initial position, 28.95 seconds for the time, 0.00155 for the acceleration, and solve for the final position. We will get about 1.3 meters. So when the marble is dropped, it will drop 5 miles and only shift towards the rock by about 4 feet. That's not particularly noticeable. It's just too small of a variance to be realistically noticed by the human eye. But since in your example, you showed the marble right next to the rock as well as at a distance from it, let's say we drop it from right on the edge of the rock. That will change the radius to 2.5 miles. By cutting the radius in half, it will change the acceleration by multiplying it by 4, as can be understood by the relationship in the equation in the upper right. This will still give us an acceleration that is significantly smaller than that produced by the gravity of the Earth. What we can learn from this is that the acceleration an object receives is proportional to the mass and to the radius. Since the gravitational law constant is a constant, it remains the same in all calculations, so only the other two matter when talking about relationships. But because the radius is squared, it makes the change in acceleration geometrically proportional to the radius, while only linearly proportional to the mass. Thus, it is more important to be closer to an object than to have a bigger object when it comes to acceleration experienced. So while the gravity of the Earth is why the marble falls to the Earth, it is because of how close it is to such a large object relative to how close it is to the other object. The relationship above needs to be understood. Next, you try to correlate this by asking, if the same principles apply, why doesn't the moon get pulled into the sun when it is on that side of the Earth versus when it's on the far side of the Earth from the sun? And then you offer a second question as to why it doesn't have any speed difference when it is coming versus when it is going. I can answer this pretty simply. It does! The moon does experience a speed difference when going from its apogee to its perigee. It is moving too slowly across our sky to be noticed, but it does change speeds. I know you don't like NASA-produced information, but here shows information about the moon that indicates the moon is moving faster during its perigee and slower during its apogee, just as the Earth moves faster during its perihelion and slower during its aphelion. Therefore, you positing the question is based on factually incorrect premises. Now, To answer your first question, the moon keeps its orbit around the Earth even with the sun's gravitational effect because the change in the radius between the sun and the moon is so small. The Earth's pull on the moon is strong enough to overcome this difference. There will be a slight change in the precession of the moon, which causes its orbit to be elliptical, but the change in the pull will not be enough to pull its orbit out of whack because of the great distances between the two objects. Also, not forgetting to mention the fact that while the moon experiences an orbit around the Earth, it also has an orbit around the sun, an orbit that is effectively the same as the Earth's orbit around the sun. So even though linearly the sun may have a stronger gravitational pull on the moon than the Earth has on the moon, it will still stay in orbit because of the angular velocity and centripetal force that it experiences while orbiting each of these objects. Now for your shadow questions. I can tell you are making a grave error in this concept. A shadow does not always form a cone going outwards from the object. I will show you some examples. First, we will have a small light source with a moderately sized object. On the screen, in the back, we can see that the shadow created is quite large, just as you model. However, when we change the size of the light source, now to a large light source, the shadow created is now very small. The shadow cone will now get smaller to the point where it will no longer exist. So a cone is created, but in the other direction. In fact, a cone will always be created by a spherical object unless the source and the object are effectively the same size, in which the shadow will become a cylinder. Now let's look at your model. Look at the size of your sun. It's massive up in the corner. Try drawing some sightlines that would be created by your sun on your Earth and moon. It will form a cone, but in the opposite direction than you posit in your graphic. Creating a massive sun that is far away from the Earth and a moon that is relatively close to the Earth, we can see a shadow, like we might in reality. Of course, neither of our models can be to scale. We have to take a trip to Dallas and ask Jerry Jones very nicely to use AT&T Stadium's Jumbotron to have a screen large enough that would be able to represent the sizes and distances of the sun, Earth, moon, and shadows that would be created by these objects. And we can't realistically do that. You see, the grave error you made is that the cone of shadow you posit is one that exists if the sun is smaller than the object casting a shadow. In reality, the sun is so much larger than the Earth and moon that the shadow zone that would be created would be a cone that gets smaller, not larger, as you show. And your basketball example is a bad example because to get a light source that is comparable to the sun, you would need a massive light bulb, whereas people at home would try this using a small incandescent or a CFL, which doesn't represent a realistic model. As a late addition, I will comment on the image you sent around in the comment section as an explanation for your cone shape of shadows. You are claiming that it is a cone shape, but in reality, it's just a change in perspective. The shadow appears to be getting bigger, but it is simply getting closer to you. When things are closer to you, they seem to be bigger than when they're further away from you. It is all a matter of perspective. If we were to zoom out much farther, the shape of the shadow zone would actually be very close to cylindrical. Over a long enough distance, it would be a shrinking cone, but that distance is so large you wouldn't realistically be able to see it. But again, it is all about the perspective of it appearing to get bigger, but only because it's actually getting closer. I hope you can respect the fact that there have been no insulting, name-calling, or anything else in such a manner, just physics and math. I don't know everything, but I would be happy to try to answer any other questions you may have in the area.